Yo le envié mensajes, pero no han contestado.
Today we're covering the consumption function, and then we're going to cover stochastic processes, random walks, maybe covered in econometrics, I'm not sure. This isn't part of the class, or the second part isn't part of the class. Are you guys hearing an echo or somebody else talking?
What?
Are you guys hearing somebody else talking?
No.
Se escucha como un eco.
Maybe it's my.
Okay, well, it stopped. Okay. As I said, the second part of the lecture isn't part of what you'll be tested on. It's just basically background for what we'll be doing when we talk about rational expectations. So let's begin. Consumption function. If you remember, we talked about the Klein-Goldberg model, right? Basically, we have consumption equaling current income in two, excuse me, in two sectors. In this case, non-farm and farm, and lagged consumption. So consumption not only depends on income, but it depends on what consumption was last period. Actually, I misspoke. We skipped this part of the lectures, so we haven't covered it yet. But it's pretty straightforward. As I said, consumption, he has it as a function, or they have it as a function of non-farm income, farm income, and lag consumption. And that's basically because they saw that lag consumption, right, was important. That was just by data mining, looking at the data. We can speculate that they got it from Keynes out of some theory, but my guess is they got it looking at the data. So we look at quarterly GNP, the data estimated. The residuals are serially correlated. That means it has autocorrelation. We have persistence and consumption over and beyond the dependence on income, as excuse me, the equation shows. So we introduce lag consumption, right, as a right-hand side variable in the regression to account for the dependence of lag consumption on itself, and that helps remove the serial correlation. The basic regression is just consumption on a constant and income. But this, of course, as we said, is going to have autocorrelation because consumption depends on past consumption. Right. Past consumption on the right-hand side, right, basically turns it into, we've been talking about, a stochastic difference equation with income as exogenous variable. From a theoretical point of view, the short-run effect of income changes on consumption will differ from the long-run effect, right, and we'll talk about that a little later in more detail. With lag consumption on the right-hand side, we can think of consumption as the average of last period's consumption and current period's consumption, so that consumption responds to changes in income slowly. And as I said, we'll talk more in detail about why that is. Right? In this case, we split income into farm and non-farm, and like I said, you can say you got this from Keynes, but in general, they probably looked at the data and saw it. with some kind of data mining. But what that showed was that the marginal propensity to consume, MPC, was lower for farm income than non-farm income. And that's related to what we're talking about here, right? With consumption changing or responding slowly to changes in income. And as I said, we'll talk about that. So the estimated regression function is a good fit for the data, but basically we didn't have any real theory as to why. So we don't know why we put in consumption on the right-hand side, other than it fits. It fits the data. We have no reason to believe that the estimated parameters in the equation will remain fixed when exogenous variables change, when income changes. Alternatively, we have no basis to predict how they will change for movements in exogenous variables, and that's what theory is for. Presumably, an important reason for modeling the economy is that it enables us to predict the effect of unseen changes on exogenous variables. If we're just looking at data, it doesn't tell us what to expect when things change, right? In particular, we have to determine the effects of what we hope might turn out to be important exogenous variables amenable to government influence, such as monetary and fiscal policy. Right? How can we get monetary and fiscal policy to affect consumption, and hopefully GDP? So in order to have confidence in our model, it has to have at least two things. It has to be capable of refutation by empirical evidence. In other words, when we test it, we find evidence for it, and we don't find evidence against it, and it survives many attempts as such. Right? So basically what we need is something that has a good fit to our regressions, right? But we have no theoretical basis, so it's not very satisfactory. So we need basically theory to tell us why these parameters are what they are. So not only will it restrict the range of acceptable parameters, hopefully, it also allows us to compare evidence obtained from estimating the equation with evidence obtained from alternate independent sources. In other words, we should be able to prove this with different data from different countries, different mechanisms, etc. So for macroeconomics, the theoretical foundation for the particular equation might often produce implications that can be tested with microdata. In this case, right, Friedman came up with the permanent income hypothesis, right, which basically says that consumption depends on wealth, lifetime wealth. In other words, just because for some reason you don't have the income this period that you did or that you do for most of your life doesn't mean your consumption's going to fall in line with your income. You're going to smooth that consumption over time, because you know in the future your income's likely to increase. Same thing if you have a one-time windfall. You're not going to spend all that money right away, and even if you do, it'll probably be on something that you can use over a long period of time. You're going to smooth that consumption over time, and that's what the permanent income hypothesis basically says, and we'll talk about that now. Right. Suppose we have a utility function where utility depends on basically consumption over your lifetime. And it's subject to an intertemporal budget constraint, which we're going to call wealth, right? So we've already seen this type of budget constraint, right, over your lifetime, and we just call it lifetime wealth. Right? From the assumption that U is homothetic, that's basically monotonic and keeps going, in consumption at different points in time, we can assume that, or deduct that current consumption is proportional to wealth. By the way, this, if you don't remember from your math classes, that little, let's call it an infinity sign with part of it cut off, denotes proportion. So consumption is going to be proportional to wealth. So in this case, that proportion, we're going to call it K, right? So C equals to K times W, where K is a function of the interest rate. So he argues that K should be a stable function, and what changes is wealth. Next, he introduces that concept of permanent income, which we basically showed. It's what he calls wealth. He's going to collapse it into a stream of income. His idea is that consumption should be a function of this permanent income, which he can think of normal or expected, right? Even though your current income might deviate from that permanent level, as long as you rationally believe that it's a temporary deviation, your consumption shouldn't change much. So the idea is that consumption is based on what you might reasonably be able to expect to consume on an ongoing basis. And temporary deviations from that income don't affect the individual's assessment of his long-term income flow, hence his wealth, and therefore it doesn't affect his consumption. So Friedman came up with the model, and this basically won him a Nobel Prize. So I have consumption is equal to KR times YPT, where YPT is permanent income. We can think of regular income, YT, is equal to YPT, which is permanent income, plus YT, big T, little t, where this, Y big T, little t, is temporary income, right? And your temporary income is uncorrelated with permanent income, and are uncorrelated over time with lags of itself. Basically, what he's saying is it's IID. So Friedman argued that income is likely to vary much more than the real interest rate, so that explaining, right, consumption in any one period, we can take K, the proportion of income that you consume, as approximately constant. So using his model, right, he was able to explain why regressions on CT, on current income, gave a non-zero intercept, or why the why the marginal propensity to consume was greater than the average propensity to consume. Let me remind you what the difference between those two are. The marginal propensity to consume is just the percentage of income that you consume from that last dollar that you earned. So if I make $100 extra, excuse me, this year, and I spend 90, then my marginal propensity to consume in that case would be 0.9. The average propensity to consume is just that. It's the average, right, of consumption, or your average consumption, divided by your income. So that's your average propensity to consume. So if we estimate the regression, the normal regression that we had, where consumption is straightforward a function of income, right? We can write beta 1, or estimates of beta 1, as follows. It's going to be the covariance of CT divided by YT over the variance of YT. Now this is straight from any economics textbook. That's just the definition of beta 1. The covariance of CT and YT is going to be, according to Friedman, K, the proportion of income that you consume, times the variance of permanent income, divided by the variance of permanent income plus the variance of temporary income. And I can rewrite that as follows: that K equals 1 over 1 plus the variance of temporary income over the variance of permanent income. And since this is less than 1, this is going to be less than K. So the estimated value of our parameter beta 1 is going to be less than k. That's something we can test. If the OL estimate of beta 1, I'm sorry, of the intercept beta 0 is going to have the expected value of the average of consumption, C bar, minus the expected value of beta 1 hat, Y bar, where Y bar is the average, our average income, right? Since I can, since I'm assuming I can take Y and divide it into permanent and temporary, I can take this equation and do the same. So I can rewrite this as K minus the expected value of beta 1, YP hat, where this is the average of permanent income, minus the expected value of beta 1 times Y bar T, where this is temporary income. And of course, this is going to be positive. For any permanent income, it's positive. And we're going to assume that the average temporary income is 0. And when I say we assume that, it's because it's that by definition, because temporary income, right, if it was either positive or negative, would be part of your permanent income. By definition, those temporary shocks have to equal 0. Otherwise, they're not shocks, and they're not temporary, but they're part of your permanent income. So if I get that $100 extra this year, but I know I'm not going to get it ever again, well, that's temporary income. Now, if I got that $100 and I can expect to keep getting it, well, that $100 becomes part of permanent income. So thus a regression of CT against current income with all our assumptions here and our results. So CT against YT is going to yield a relationship by a flat line in the following diagram. Even if the true relationship between consumption and permanent income is as he proposed, with the steep line, or excuse me, with an origin at 0, or the intercept. On the other hand, Friedman's theory also enabled him to explain why consumption functions estimated on data over a longer period produce smaller estimates of the intercept, i.e. closer to 0, as he said, and larger estimates of the slope. That is because in the long run, your income, right, is smooth, and basically most of what you consume is your permanent income. And it didn't matter if you did it with quarterly or annual data, or even monthly data. So averaging income data over a large number of periods produces an average transitory income close to the mean transitory income, which is 0. The mean, right, can be non-zero, otherwise it would be incorporated into permanent income. Just what I explained a while ago. Okay. So if I take the average of my total income, as I said, I can split it up into the average of my permanent income and my average of my temporary income. So that's YP bar plus YT bar, and of course that's going to equal YP bar because YT bar is equal to 0, right? As n goes to infinity or as it gets bigger. So I average consumption over the same period is going to yield, right? So my average consumption is going to equal K, the function of R, times my average permanent income. So the regression on average consumption on average income will yield the estimate of the slope closer to K, right? And an intercept closer to 0. So K, right, is going to be our slope, and our intercept is going to be 0. Right? And in general, that's why, well, that's why logically K has to be lower than beta 1 in our, excuse me, in our basic regression of consumption on income. So here's the graph. Here is the last equation we talked about, where CT is basically equal to KYTT. It starts at the origin and then has a slope of K, right? And that K is greater than beta 1. Here we have a positive intercept, beta 0, right? And a slope that is less than K. Okay. Questions?
No, right now we don't. I don't have questions.
Okay. Everybody's with me. Anybody know what happened to Gisela?
No, I didn't have information about Giselle. Maybe
I sent her a message,
she's
but
working.
she didn't answer.
Okay. Can you guys give me a second? My son's calling me.
Okay.
Hey, buddy, what's up? Hey, okay. Did you get my email? Did you get my email? Okay. Basically, buddy, I'm giving class right now. As soon as class is over, I'll go get you. No problem. I'll call you. I'll call you when I'm going to get you. All right. Should be over in about an hour. I'll give you a call, buddy. All right. Okay, I'm sorry about that, guys. He was getting out early today, but he couldn't tell me till later this morning. Okay. Okay. So Friedman's theory basically also enabled us to explain why estimates of the marginal propensity to consume out of farm income were lower than the marginal propensity to consume out of non-farm income. And that's simply because farm income has a lot of variance. It depends on the price of the crops, on your harvest, etc. And whereas non-farm income was much more stable, had less variance. So basically, farm income has more variable than non-farm income, and the ratio, the variance of temporary income to permanent income, is greater. So increases in the estimate of K from this decreases. Hence, the estimate of marginal propensity to consume out of farm income would be lower than estimates of the marginal propensity to consume out of non-farm income, which makes sense because their non-farm income is more variable and not as certain. So therefore, when you have a shock to your income, and you're a farmer, well, that's likely to result in you decreasing the amount of your consumption. Right? So he examined a cross-sectional data set and showed that the estimated marginal propensity to consume could be related to variances of income over a wide range of different occupations, not just between farm and non-farm income. So any occupation that has more variance in income is going to have a greater marginal propensity to consume. Right? To explain the cross-sectional evidence, Friedman didn't have a specific form for permanent income. He merely needed to argue that income streams with higher variance also displayed higher variance of temporary relative to permanent income. However, to examine the time series evidence, he needed to specify how permanent and measured income were related. Right? So as in Kagan, that we did study, of expectations formed for hyperinflation, Friedman assumed that expectations of permanent income were formed adaptively. Right? So your permanent income was some function of your permanent income last period plus your current income. And of course, this current income is part of your permanent income, part of your temporary income. And he used lambda, so 1 minus lambda times permanent income last period plus lambda towards your total income this period. So he substituted his definition into the consumption function and chose lambda to yield the highest R squared. Basically, it was sort of like an F-sup test, an F superior test. And an F superior test is where you basically data mine. You run a bunch of regressions and you pick the one with the highest F statistic. or the most, excuse me, the most significant error statistic. And that's basically the same thing as getting regression with the highest R squared. So however, using a lag operator, we can rewrite Friedman's definition of permanent income as follows. And you guys remember the lag operator. So I basically take that part of permanent income and put it on the right-hand variable. If we really wanted to be technical, I could break this into temporary and permanent income, but then we'd end up with something that equals 0, so it wouldn't help us much. So here, I just take lag permanent income, I put it on the left-hand side, and I get 1 minus, or I eventually get, after working lag operator, 1 minus lambda times lag operator times permanent income equaling lambda times total income. So therefore, I can solve for permanent income, excuse me, as lambda over 1 minus lambda L for the lag operator times current total income. Right? So now I substitute that into our consumption function, the basic one that we had, and multiply through by 1 minus 1 plus lambda times our lag operator, and I get the following: CT minus 1 minus CT. By the way, this is the equation with lag, consumption, and income. So I got CT 1 minus lambda CT minus 1 equaling K lambda YT plus UT plus 1 minus lambda UT minus 1. Well, this is going to be our error term in our, excuse me, in our regression. Actually, not yet. Let's go through. Like the Klein-Goldberger consumption function, except now we have an intercept, I'm sorry, an interpretation for the coefficient of lag consumption on the right-hand side equation. Furthermore, by the way, there's a footnote there. Furthermore, we have the restriction on the coefficient of income and lag consumption, right? The coefficient of income should be K times 1 minus the coefficient on lag consumption. Therefore, we can use long periods of data or cross-sectional evidence to provide an alternative estimate of K, against which we can check our estimates from the short period of time series data. Finally, the cross-sectional evidence presented by Friedman justifies us breaking income into its farm and non-farm components, as Klein and Goldberger did. So the permanent income hypothesis has given us some mileage in explaining data. We can go further in obtaining an interpretation from our parameters for lambda by considering the concept of rational expectations as proposed by Muth. So we'll do this in the next chapter, or next week, when we talk about rational expectations. And there's a footnote from here, right? So the Klein-Goldberger consumption, except that we know we have an intercept for of lag C on the right-hand side of the equation, right? So the main difference between the equation derived here and the Klein-Goldberger equation is that the error term, this thing, will be autocorrelated if UT or white noise, while in Klein-Goldberger, the service must have a first-order autocorrelation if the parameter estimates are to be consistent. And that's just econometrics, but the theory is pretty much from the permanent income hypothesis. And that is our lecture on consumption. It's a short lecture. Usually what I do with this lecture is I go through this and then I start on the, excuse me, I start on the rational expectation lecture. And halfway through the rational expectations lecture, I talk about stochastic processes. Now, since we're actually going to meet in person next week, I deduce that it's probably better if I cover rational expectations in person. And instead of breaking the rational expectations lecture in half like I usually do, is I just talk about stochastic processes now. It's fairly straightforward. It's fairly simple. It comes from physics, but it's not really complicated. What Jose Cao has given you so far is much more complicated. But suppose we have a stochastic process, right? And that process is one where the variable in question changes in uncertain ways. That gives us a definition, what we're going to call the Markov property. A Markov process is a stochastic process where the only variable relevant to prediction future values is the independent variable of today's value. In other words, past values, t minus 1, don't affect the value next period. And t plus 1, only the present one does. And for those of you guys who know a little bit of finance, this represents weak form efficiency market hypothesis. Right? The next thing I want to talk about is a Wiener process, or what we call Brownian motion. This is from physics, right? And it was used initially to describe motions of a particle that is subject to a large number of molecular shocks. In other words, other molecules banging into to other molecules, so banging into one another. In this case, there's no way to tell how the particle will move in response to another particle smashing into it. Therefore, the best guess for the particle at period t plus 1 is its position at time t. So if you have a molecule and you observe that molecule, right, and other molecules are banging into each other next to it, your best guess for where that molecule will be next period is right where it is right now, right? And this is a particular type of Markov process, right, the Wiener process. So what I want to do is I want to define z, right, as a variable which follows a Wiener process, right? Therefore, small changes in t, right, time, the change in z can be denoted as follows. So a change in z is going to equal to some coefficient, and we'll call it epsilon, times the square root of the change in time, right? Where epsilon is standard normal, with mean 0 and variance 1. Right? So the value of changes in z is independent of independent of one another for any small interval of time or any small change in t. Since epsilon is standard normal, right? That's with mean 0 and variance 1, and t is strictly increasing. In other words, time can't go backwards. It follows that changes in z are also going to be normally distributed. The mean of changes in z has to be 0 because we assume that, right, your best guess is where it is now. So the mean of changes in z is 0. The standard deviation of changes in z is simply going to be the square root of changes in time. And therefore, the variance is simply going to be changes in time, delta t. Now we can start thinking of longer time periods instead of those really short time periods. We call it capital T. Capital T is the sum of equalized changes in small t. So capital T is basically the summation of a bunch of delta t's. So now delta z can be denoted as the difference between time at period capital T and time 0. So I can denote change in z as z of capital T minus z of 0. And that's going to equal the following, right? Z of big T minus z of 0 is going to equal the summation epsilon 1 times the square root in the change in t. And that's basically just we're taking the summations of a bunch of smaller periods, just like we assumed right here, and of course taking the definition of the variances and the means. The definition of a small change, a change in z over a small time period. So I sum up all those small time periods to get the larger time period, and this is what I get: the summation of epsilon. By the way, that's epsilon I I said epsilon t a while ago, I think. So epsilon I times the square root of delta t, where n is equal to big T over delta t, since each has equal size, and I goes from 1 to big N. So our epsilons are our IID, random samples of a standard normal distribution. That means they're identically independently distributed with mean 0 and standard deviation 1. So if a dependent variable equals the sum of an IID normally distributed independent variable, then the dependent variable is also normally distributed. The mean will be the sum of the independent variable, and the variance will be the sum of the independent variables. However, the standard deviation of dependent variables will not be the sum of the standard deviations of the independent variable. Just the mean, and you guys should know that when you work from means to variances. But rather it'll be the square root of the variance. So here we're going to have the mean, zig big T minus C of 0, that's going to equal 0. The standard deviation of that big time period is just the square root of big T. And the variance is just going to be the square of that, or n minus delta T, which is big T. So now I can write the equation in continuous time, right? With infinitely small intervals, right? So instead of going from a summation, I can go to an integral. So I'll get the change in z is simply equal to epsilon, the square root of the change in t. Just like before, this has mean 0 and variance 1, so it's still standard normal, which means z has a future expected value equal to this period's value. That means our best guess is what it is today, and a variance of 1. And that means that the variance of the change in z in a time variable big T is simply 1 times t. So this equation that mimics a random walk with the drift. That is just a random walk. I'm sorry, a random walk without a drift. It's just a standard random walk. In economics and in finance, basically when we talk about random walks, it's almost always with a drift. In this case, it's just a strict random walk. Your best guess is what it is today. Right? So basically, when we have random, excuse me, a random walk with the drift, we expect current values basically to grow, and we expect it's going to grow with whatever the drift is, and that drift is going to have a covariance. And deviations from that drift, however, are going to be unpredictable, and therefore deviations from the drift, right, or changes in deviations, or deviations from the drift, sorry, are going to have an expected value of 0, just like up here. So our best guess from a deviation in the drift is simply 0. Okay, so now we want to talk about a random walk with the drift. So I can generalize the Wiener process as follows. Instead of just z, I'm going to say our change in x, some variable, is going to equal a times change in time, dt, plus b times dz, where zz is our Wiener process, which we can write as follows from before, because I know dz is equal to epsilon, the square root of dt. So I have dx a dt plus b epsilon, the square root of dt. So if epsilon dt equals d0, right, that equals 0, which we know it's by assumption, and therefore a is going to determine our drift, which means the mean of dx is going to equal a dt, right, where a is equal to dx dt is our drift. This means that each period x is expected to grow by a, Therefore, the expected value of x at time t will be x equals x0, where it started, plus at, where x0 is the value of x at time 0. So now I can write the first and second moments of the actual values as follows. The mean of x is simply a big T. The standard deviation of x is b, the square root of big T. And the variance of x is b squared T. Basically, this is pretty much the same as our other Wiener processes. The standard deviation variance looks almost exactly alike, except we're not using epsilon, we're using b. And the mean is no longer 0, but now it depends on the drift. A big T. So our first and second order moments of the change are as follows. The mean of dx is a dt. The standard deviation, right, of the change in x is b, the square root of dt, and the variance is b squared dt. To be formal, we should actually use discrete changes, but you got the idea. Next, we're going to talk about an Ito process, and I'm not sure I'm pronouncing that right, but I think so. This process assumes that the coefficient of a and b are dependent on time, and that the dependent variable t. So here in the Ito process, dx is a dt just like before, but here a is also going to be simultaneously a function of x and t, plus b, where it is also a function of x and t dz. So this is exactly like before, except now the coefficients are actually functions of both x and time. So therefore, the coefficient, the drift, and the variance can change over time, right? When x and t change. Okay. Questions? Anybody? Okay. Back to our lecture. Talk about stock prices. Now, you might think this is finance, but this works for all of macroeconomics, basically. Not the theory, but the Ito and Wiener process. Investors demand a certain return for a given level of risk. Therefore, we can use the simple Wiener or Ito process. There the drift must be proportional to stock price, so we can write the drift as mu s, where s is a stock price and mu is a constant parameter that represents the return on stock. Now we can write a more complicated Wiener process where I have the change in s ds is equal to mu s dt plus b dz. So this is the same as before, except for having a coefficient here, alpha, we have, I'm sorry, a, we have mu s. If dz equals 0, which it should by assumption, then ds is equal to mu s dt. And I can write dss equal to mu ds. Let's talk about. And therefore, I can write s as, in continuous terms, as S0, where S0 is the stock price at time 0, the exponent mu t, right? In other words, I want mu as a continuously compounded growth rate. So note that this is similar to what we had before, x equals to x0 plus at, but now we're compounding the growth. But the process is the same. So although the expected value of DC is 0, it won't always be 0, right? And therefore it has a variance. So to get that, I want to define the variance of S, the stock price. Therefore, the variance of the proportional change will be the variance of S, dt, and the variance of X and the actual variance of actual changes is the variance of S times S dt. A lot like before, instead of now, we have that initial, well, we have that current stock price. So now I can write the stochastic process for the stock as follows. ds equals mu s dt plus sigma, where sigma is the standard deviation of stock price, s dz. And I divide both sides by s, and I get ds over s, or the proportional change in x, is equal to mu dt plus sigma dz, right? So here, b up here is replaced by sigma ss, or the standard deviation of s times s. So now we can write it as follows, right, as we did before. Well, similar to what we did before. Right? So I have ds over s is equal to mu dt plus sigma, and I want to substitute dz for mu, the square root of dt, right? All this is, or what this is a type of process, so type of Warner process, right, that shows us in finance what we call the weak form EMH, or weak form efficiency market hypothesis. That is, the best guess of returns from period t to t plus 1 is simply the return from period t minus 1 to t. Or in other words, s times the drift, or the price today times the drift. And you get the drift from t minus 1 to t, or you estimate the drift from t minus 1 to t. Okay. As I said, that stochastic process isn't going to be on the test. Are there any questions?